Now let's consider the curve, parametric curve, where x is given by t multiplied by t squared minus 3 and y is given by 3 multiplied by t squared minus 3. And to start with, we are asked to find at what points we have horizontal or vertical tangent lines. And then we'll try to sketch the curve using, among other things, this information. So to see where the tangent line is horizontal or vertical, we want to see where this dy over dx obtained by dividing y prime of t by x prime of t is either 0 or going to infinity. So y prime in this case is a derivative of 3t squared minus 9, and that's just 6t. And x is t cubed minus 3t, so its derivative is 3t squared minus 3. So we can factor out 3 at the bottom, cancel it out with writing 6 as 2 times 3, and we obtain 2t over t squared minus 1. Or in other words, 2t over t minus 1 t plus 1 if I factor out the denominator. So now in this form it's easy to see when this quantity is 0 or infinite. It is 0 exactly if t is 0, because it's going to be 0 when the top is 0 and the bottom is not. And therefore we have only one horizontal tangent at the point of coordinates x of 0, y of 0, and when I plug t equals 0 in the functions x and y, I get 0 for x and negative 9 for y. So we have an horizontal tangent at the point of coordinate 0, negative 9, which is on the curve and corresponds to the parameter t equals 0. On the other hand, dy over dx, as you can see, is going to be infinite when t approaches plus or minus 1, because this makes the denominator 0 and the top non-zero. Therefore, we're going to have vertical tangents for t equal 1 and t equal negative 1. The corresponding points on the curve are obtained by plugging t equal 1 and t equal negative 1 in the functions x and y. So when we plug t equal 1, we get negative 2, negative 6. And when we plug negative 1, we obtain 2, negative 6. So at these 2 points, we're going to have vertical tangents. So what this looks like is this. We have these 3 special points, 0, negative 9 where we have an horizontal tangent, negative 2, negative 6, and 2, negative 6 where we have vertical tangent. Well, that's a start, but certainly not enough to sketch the graph. So to sketch the graph, we discussed it a little bit in the previous video. We need to look at the increase and decrease of both x and y, and then follow along in the xy plane the changes of x and y. So we've already calculated x prime. It's 3 multiplied by t minus 1 t plus 1. Y prime was 6t, so this is going to help us see the increase and decrease for x, namely x prime is going to change sign at negative 1 and 1, y prime at 0, and the sign of x prime and y prime is going to give us the intervals of increase and decrease for x and y. So for x prime, I could have written the sign of t minus 1, the sign of t plus 1, make a table of signs to get the sign of x prime. I'm going to use a geometric shortcut here. The equation of x prime is 3t squared minus 3, so this is a parabola that opens upward, looks like that, and so as you can see, it's going to have to be below the x-axis between the zeros and above the x-axis outside of the zeros. In other words, x prime is negative between negative 1 and 1, and positive if x is less than, if t is less than negative 1 or t is greater than 1. The interpretation in terms of increase and decrease is that x is increasing if t is less than negative 1 or if t is greater than 1, and decreasing between negative 1 and 1. Y prime is just 6 times t, so it is positive when t is positive. I'm sorry, I forgot to mention that we have the values, the local maximum for x of t at negative 1, which is the value at negative 1, which is 2, and the value at 1 is negative 2. This corresponds to these points with vertical tangent. At 0, the function x takes a value 0, the limit at negative infinity is negative infinity, the limit at positive infinity is positive infinity. As I was saying, the derivative of y prime is 6t, therefore it's positive for positive t and negative for negative t. That is, y is decreasing for negative t and increasing for positive t, and has minimum at t equals 0, and this minimum is the value of y at 0, which is negative 9, and corresponds to this point 0, negative 9, where we have an horizontal tangent. As we have seen, the value of y when the parameter is either negative 1 or 1 is negative 6, and that corresponds to these points with a vertical tangent. The limits at negative or positive infinity is infinity, and so we have a sketch of the increase or decrease of both functions x and y. So now we can try to follow along what happens. So let's look at this interval for the parameter t, where t is between negative t and negative 1. Then x of t comes from negative infinity and y of t from positive infinity. So we come from the top left corner of the picture, and x increases, in other words, moves to the right, while y decreases, in other words, moves down. So we get something like that. And x is going to increase all the way up to its local maximum value of 2, while y decreases down to negative 6, which is a situation when t is negative 1. So we get something like that. And then we approach this point of coordinates 2, negative 6, corresponding to t equal negative 1, with a vertical tangent. Then, when t is between negative 1 and 0, you see that x now decreases from 2 to 0, while y continues to decrease from negative 6 to negative 9. So both x and y decrease, and the curve is approaching this particular point of coordinates 0, negative 9, corresponding to the value of the parameter 0, and where we know we have an horizontal tangent. So we get something that looks like that. Now if we turn to the next interval, where t is between 0 and 1, we see that y is now increasing from negative 9 to negative 6, while x is decreasing from 0 to negative 2. And so y is increasing, x is decreasing. We're going towards this point where we have a vertical tangent corresponding to the value of the parameter t equal 1, and that looks like that. And now if we go to the last interval, both x and y increase, and both go to infinity. So we get something like that, because we have to go towards the upper right corner when both x and y go to infinity. Now you note that we should have a point of self-intersection somewhere around here. And so this is an important point, an important feature of the curve, so we need to find out the coordinates of this point. So how do we do that? Well, if we have self-intersection, it means we go through the same point of coordinates xy for two different values of the parameter. So we have t1 and t2, for which x of t1 is equal to x of t2 and y of t1 is equal to y of t2. So this is what I have written here. What it means for x of t1 to be equal to x of t2 is the first line, and what it means for y of t1 to be equal to y of t2 is the second. If you look at the second line, of course we can cancel out the 3, and so we have equality between t1 square minus 3 and t2 square minus 3. If this quantity, which is the same on both sides, is non-zero, then we can cancel it out in the first equation, right? Divide both sides by this quantity, and then we would get t1 equal t2. But of course we are only interested in the case where t1 is not equal to t2, because we want two different parameters where we end up in the same point. So because t1 is not t2, the only possibility is that t1 square minus 3, which is equal to t2 square minus 3, is 0. In other words, t1 and t2 are the two roots of the equation t squared minus 3 equals 0. That means they are negative root 3 and positive root 3. If we plug t equal negative root 3 or t equal root 3 in x and y, the point that we obtain is the origin, the point of coordinates 0, 0. In other words, our curve needs to be adjusted like that. It goes through 0, 0. This is this double point, this point of self-intersection. Now to complete our sketch, because this is an important feature of this curve, this particular self-intersection point, we will need to have the tangent lines at that point. So to do that, we go back to our formula for the slope of the tangent line and we plug the value of the parameter, which is negative root 3 and positive root 3. And we obtain that at positive root 3 we obtain root 3 for the slope of the tangent line, and at negative root 3 we obtain negative root 3 for the slope of the tangent line. In other words, we get these equations for the tangent lines. Right? When we go through the origin the first time for parameter t equal negative root 3, we go with a slope of negative root 3. When we come back along with value of the parameter positive root 3, then we go with a positive slope of root 3. And now we can look at a nicer sketch of the graph. Now that we have all that, we could redraw our picture in a more smooth way, and this is what we would obtain. Now let's turn to the next video to look into other types of things that we can study about the parametric curve using calculus.